Any feedback from the quiz on Friday? How was it? What? Was it all long? It was long? Yeah. Yeah, sometimes when you get with these matrix problems, the problems look long, but hopefully you saw that I think the first problem had 2 degrees of freedom and the second problem had 1 degree of freedom really that you had to calculate. But yeah, I'll discuss the solutions for the quiz, and I hope that you got a chance to at least attempt all the problems, and of course, as usual, I have partial marking. Other than that, I think aside from the quiz, we'll have a homework 9 that we'll assign today. That homework would be based on the topic that we started actually before the quiz that I hope you finish today, which is stiffness method for beams. And then there'll be one last homework 10 and then the final exam. Okay. There are a few extra handouts from the last time's lecture. In case you didn't pick one up, there were 2 handouts last time. I guess that was last Monday. There's another new handout that I've just given out. So if you don't have that handout, you can come up and pick. And what we'll do is, if you have any particular questions, I'm happy to take them. Otherwise, we'll jump right into the stiffness method for beams. Any questions from, well, I guess what I'll do is I'll do a quick review of what we talked about for stiffness method for beams, and then we'll see if you have more questions. So, as I said, last time we started this topic on stiffness method for beam problems. And I told you that beam problems are basically problems where we have some sort of a beam, which is usually we take the horizontal direction as the orientation. Could have multiple different types of loads, multiple different types of support conditions. Here's the first question: is this particular beam, is that statically determinate or indeterminate? Determinate, right? It's a simply supported beam with an overhang and with a tip load. So it's a determinate problem. You can solve for all the reactions, bending moment diagram, shear force diagram, everything using statics alone. Whereas for an indeterminate problem, statics alone does not work, as we saw. And I also mentioned that for the stiffness method for beams, and for stiffness method in general, it does not matter whether a structure is statically determinate or indeterminate. It's the exact same method that works on both types of problems. And really, what we have for stiffness method of beams, we have 2 degrees of freedom per node, which I think I had marked below here, for example. At every node, we have a vertical or a transverse displacement that is usually a degree of freedom, and the rotation at that node, that is a degree of freedom. So again, just like truss problems, we have 2 degrees of freedom per node, but the meaning of that degree of freedom is different. So last time we were in the middle of trying to derive the force displacement relationship for a beam element. I told you last time that if you have a beam structure, the first thing we do is we divide it up into a set of elements, which obviously have 2 nodes at their ends. And then we try to figure out how is that beam element going to behave under some applied loading. And I said that if this is, for example, one beam element, then in general, it could have some vertical displacement at node I, another vertical displacement at node J, some rotation at node I, a different rotation at node J. So in terms of those 4 degrees of freedom, delta I, delta J, theta I, theta J, we can express any configuration of that beam element. And the idea was that given these 4 degrees of freedom, these displacements and rotations, given these 4 displacements and rotations, we want to find how they're related to the transverse shear force at the 2 ends and the moment. I'm not going to call this bending moment because this is not really bending moment. This is the nodal moment. Okay, so this is nodal moment MI mj, and transverse force qi and qj. So we said that if we can figure out these four particular cases, how the beam element responds in these four cases, then we can combine them in different ways to come up with the response in a general setting. So, for example, if I know that the beam responds in this manner, if I give a delta I displacement at node I, it will respond like this, where I can calculate mi, which we did actually last time. So I'll show you that in a minute. Um, I can calculate what that node moment would be. I can calculate mj. I could calculate qi and qj. So I know the response of this beam under delta I. Similarly, if I do the calculation for case 2, where I know the response for theta I, know the response for delta j, know the response for theta j, I can combine them in the right amounts to come up with the response for a general beam element under general loading conditions. So that was the overall idea of the stiffness method. Very similar to the truss problem. Break it up into elements, find out how each individual element behaves. That is the local element force displacement relationship. Assemble all of that and enforce equilibrium to find these displacements and rotations at the nodes. So that's what we were doing last time. And last time we went through this case 1. So case 1 we derived last time that if I give you a displacement delta I, what would be these four nodal moments and nodal forces? And you remember last time we had to break it up into two parts because really this is an indeterminate structure. This particular case 1 response is an indeterminate response. So we break it up into the underlying determinate and the redundant structure. We use compatibility to solve for all the reactions. And using that, we were able to come up with this relationship that these four quantities, Qi, Qj, Mi, Mj, were equal to some factor times delta I, meaning that if I give delta I displacement at node I can tell you exactly what those four values are. And one neat thing that we did last time was to try to express these four relationships in the form of a matrix, which will come in handy later on when we have all the four cases that we want to combine. So in this case, you can see that I have the displacement and rotation vector, where all the other degrees of freedom are 0. The only degree of freedom non-zero is the delta I for case 1. And what we did was we calculated Qi, Mi, and expressed them in this matrix form. So you can see that the first column up here, the first column has these four values. And obviously you can check that this column or this row multiplied by this column or this vector is what you would get up here. So it doesn't really matter what these other three values are because they are 0 here. They are being multiplied with 0. That gives you these four relationships. So that's what we did up until last time. And if you have any questions about this process, I'm happy to take it. Otherwise, as I mentioned last time, we'll try to do case 2 as an in-class assignment. Okay? Any questions on this? If not, then let's go to case 2. So what I'm asking you to do for case 2 is solve this problem. You have a beam element which is pinned at left node and it is fixed at the right node. So the only non-zero degree of freedom is theta I. Okay? And maybe I'll phrase this problem again in a slightly different way. So, yeah, please do take a separate piece of paper and don't forget to write your name on it. The question that I'm asking you to solve is that if I apply a moment mi here, I'm going to get some rotation theta I, correct? So if I apply a moment mi here, relate what would be that theta I basically. Apply moment mi here, find theta I. That's all I'm asking you to do. And then in terms of that theta I, find all the other three forces and moments. So the problem is applied moment mi, find theta I. So let's take 5 minutes, maybe take a couple of minutes to try it by yourself and then discuss with your fellow students. And then I'll take it back up here. And if you have questions, feel free to ask. Yeah, feel free to discuss amongst yourselves as well. Right, what questions are we coming up with? Go ahead, Joe.
How does your system differ from the first case?
The system is different from the first case because of the loading conditions. The first case was where I have a vertical ruler at the left. So there's a non-zero displacement, but the rotation here is zero, right? So maybe we can take a look at all the four cases all at once. The response in case one is where there's zero rotation but one displacement here. Here there is rotation but no displacement. And here there is displacement at J, but every other degree of freedom is zero. Here we have rotation at J, positive rotation at J, but every other degree of freedom is zero. So um, I'm not sure if that's what you're asking.
It's more of the underlying determined systems of the thing is a fixed moment.
Okay, yeah. So all of these four cases are actually indeterminate. They are indeterminate to degree 1, right? So you should be able to use the same sort of logic that we used for case 1, except now that the load and the boundary conditions are different. So in case 1, we solved this problem where we broke it up into two parts, one of a cantilever beam, the other with, uh, it looks like, yeah, so it's a cantilever beam with a right amount of load being applied here. So
So that your two underlying reductions are the same. It's just your moment or your angle or your displacement that's zero. Your combination.
right, so if it is a cantilever beam, then when I apply the load QI, it will deflect and the right end will have some non-zero rotation, right? So that non-zero rotation is not what I want. What my actual boundary condition is, it's a vertical roller at the left end. And to get zero rotation at the left end, I would apply some moment here. And when I add these two, I get back this structure. So that's the same sort of logic that we want to use for case 2. Dave?
Well, I'm confused with the compatibility equation of this one.
For-
It'll be a delta I prime now?
No, because here I want to make the rotation to be 0
For case 1,
for case 1.
but not for case 2.
For case 2, no, because in case 1, we want, this is case 1, we want the rotation to be 0, but not the displacement. For case 2, we want the displacement to be 0, but not the rotation. Okay. Okay, so go ahead. Question, Haim?
Trying to answer.
Oh, okay.
I'm not sure it's going to work, but I want to break it into two parts. And one is determined. I just want to make the right support to be
Pain. Right, right. So yeah, that's exactly what we are going to do. So maybe we should go ahead and try to do this together in class, and then if you come up with more questions, we'll try and take them. So for this structure, this is the problem that I'm trying to solve. I'm going to say that this is equivalent to a simply supported beam with a roller at the right end, and there is moment mi applied to it, and plus the same simply supported beam with a moment mj, which I don't know yet. I apply that moment in such a way that the rotation at the right end goes to 0. So let me explain that even more. Under this simply supported beam with this applied moment, I'm going to get a deflected shape that would be something like this, right? This deflected shape and this deflected shape that I ultimately want are of course different, because there is on the right hand side I have removed the fixed support to replace it with a roller. So the question I'm asking is now, what is the correct amount of moment to apply at the right end so that when I combine these two deflected shapes, I get the correct response. Does it make sense? So if I add these two, I should get this response. Now, so let's solve the underlying actual load problem, and then we'll do the redundant problem. So in this case, for this problem, I'll have reactions, which would be rotating this way. So this will pull down in an amount mi divided by L. This would be pushed up mi divided by L. The bending moment diagram for this first case would be negative mi and up to 0 linearly. And similarly, the bending moment diagram for for the right hand side That's a positive. And actually, okay, so and what I'll do is, instead of marking it as mj, right now I'll mark it as a unit moment, and I'll say mj times, so mj multiplied by this unit moment when added to this diagram should give me back the original problem that I was trying to solve. So this would be negative, sorry, it should be positive. It's a positive bending moment. So that's a positive bending moment. Now, the rotation at this end, at the right end, due to this bending moment diagram, how can I find that? Rotation at the right end. Moment area would not be that simple. Is there a better way? So if I want to find the rotation of a beam at one end, how do we, or if I want to find the displacement, let's say think virtual work method. So if I want to find displacement at a point, I apply unit load at that point. If I want to find the rotation at a point, what do? Apply unit moment, which is the second case, right? So in this case, the bending moment diagram for the second problem would be basically um, x divided by L, right? Um, this length here is L. So in this case, I'm measuring x from this side. So measuring x from this side as well, I would have the equation of the other curve would be mi plus minus mi plus let's see, it would be x over L times mi, right? So we can check when x is 0, the moment here is minus mi. When x is equal to L, the moment is 0, right? So these would be the two equations. And under these circumstances, then I can find theta j prime um, would be equal to integral 0 to L of the virtual bending moment, that's x over L, times the real curvature, that's minus mi plus x over L times mi divided by ei dot dx. So that would be the displacement, that would be the rotation at the right end due to a load mi applied here, correct? And that would be equal to, let's see if we can simplify this. So I'll pull out minus mi over, oops, ei, and 1 over L also comes out. Actually, I'll make it 1 over L square, integral 0 to L of x times L minus x dx. Please keep checking my algebra. I'm pulling out mi over ei, and both L's I've pulled out, so I have 1 over L square. What I'm left with is xL minus x square. So that should be equal to mi over ei 1 over L square, and again a minus sign. Maybe I'll move it. So xL would be L times L square over 2 and minus x squared would be L cube over 3. So what I get is this L square cancel off, and what I get is minus mi times over ei L over 6. Let's make sure that's correct. So, right, and maybe that would have been an easier way anyway. So let's see. Okay. All right, there we go. So in your book on the front cover, there are these tables. If you haven't used them, hopefully you know how to use them for the force method. Typically, these are not needed really because you can very easily solve for these integrals. But since we are doing this for the stiffness method once and for all, we want to make sure that we don't make any mistakes here. So the problem that we are solving is very similar to this, right? This last case here. Maybe I'll put it at the other screen too. So this last case here has a simply supported beam with a moment m0 applied at the right end. What I want to know is the rotation at the left end. Is that right? So what this formula says here, theta L, which is rotation at the zero end, is minus m0L divided by 6 EI. And if you look at what we got minus MIL over 6EI, exactly the same thing. Similarly, if you look at the rotation for this problem now, the second half of the redundant problem, if I give it a unit moment here, I want to find what is the rotation at this end. So that is something that I would call flexibility coefficient for the rotation at this end. Alpha, I'll call that alpha JJ. So alpha JJ is again something that we can read off of this table. In this case, I have a moment applied here, and I want the rotation at the right end. So in that case, that would be m0L over 3EI. Okay. So L over 3EI would be the rotation at this end, L over 3EI. Just reading off of the table from your front cover of the book. And what would be the compatibility equation, anybody? What would the compatibility equation say? Okay. It would say theta j prime, which is so theta j prime, that is the rotation here when I apply mi. April? Oops, sorry. Laptop. Yeah. Okay. Yeah. So the rotation theta j prime is the rotation at the right end when I apply moment at the node I, and that we just found was minus mi L over 6. Alpha jj is the rotation at the right end when I apply a unit moment at the right end, right? So in terms of these two things, the compatibility equation would say that in when I combine these two, the rotation at the right end should be 0. and that would basically be that theta j prime plus mj multiplied with alpha jj equal to 0, which immediately tells me that mj would be equal to minus theta I prime, sorry, theta j prime divided by alpha jj, which tells me that mj would be equal to mi L over 6 EI divided by L times 3 EI up here. So again, EI's cancel off and L's cancel off, and what we get is that this is the right end moment would just be equal to half this moment at the left end, but that still doesn't tell me anything about the rotation at the left end. All that we have done till now is we've solved the indeterminate problem here. So what I've just found is that mj would be equal to mi over 2. Now using this, I can figure out what the reactions would be, the other forces. So in this case, the reaction would be 1 over L down 1 over L. So when I combine these two, I have mi over L going up and mi over L over 2 going up. So that would be how much going up here? What would be qi? Joe? Okay, mi over L plus mi over L, mi over 2 times over L. So that would be 3 mi over 2 or 3 over 2 mi over L. The same thing down, 3, that would be qj 3 over 2 mi over L. So we have found out all the reactions at the two ends, right? Now we still haven't correlated mi with the rotation. So how can I find that? How can I find rotation if I know all the other things? Say again? No, the table does not help me there, because all of these things in the table, they are all determinate structures. So we can use moment area, or we could use virtual work, or pretty much anything. But let's see, maybe the easiest thing would be to do use virtual work, because we already know what the bending moment diagram for the real and the virtual system is. Because applied a moment here, I know what the bending moment diagram for that would be. Let's see. If I add those two bending moment diagrams, what I would get would be minus mi here and plus mi over 2 here, and a linear variation between those two. Do you agree? So that's the bending moment diagram for the indeterminate, for this indeterminate structure. And if I want to find the rotation here, I can again use the virtual work method. So theta I would be equal to integral 0 to L. I need the virtual bending moment, which would be virtual bending moment for a unit load, or a unit moment in this case. So that would be the easiest way to do that would be to express x here, and what that equation would be, sorry, I'm pointing the other way. we'll measure x from this point, and the equation for that would be mi over 2 times x divided by L over 3. Does that make sense? Let's check. When x, so hopefully you all see first of all that this is L over 3 and this part is 2L over 3. Is that right? And then if I take x equal to L over 3, then this guy goes to 1 and I'm left with positive mi over 2. Since it's a linear relationship, I'm sure it will go to the right value here, but let's check. X is equal to minus 2L over 3. What I'm left with here is minus 2, and that gives me minus mi. So indeed, that's the correct expression. So the virtual bending moment would be 3 over 2 x times L. The real curvature would be 3 over 2 x mi over L ei and dx. Hope that makes sense. And I'll draw a line between these two parts to make them separate. So we can calculate this by pulling out 9 over 4, 1 over L square, mi also comes out, and ei also comes out. What I'm left with is x square. Integral of that x square would be L cube over 3. April? You're right. Thank you. I was about to make a big mistake here. So it would be minus 2 over 3 L to L over 3. And indeed, the integral would not be L cube over 3. It is x cube from minus 2 over 3 L to L over 3, which would be mi over, or 9 over 4 mi L square ei. In the brackets, I'll pull the 1 over 3 out as well. So in the brackets, I have only x cubed now. So I'll have L cubed divided by 27 minus of minus 8 L cubed divided by 27. And what that would give me is this 3, this 9 goes away, and these numbers don't seem to be matching up. Let me check. Sorry, so it shouldn't be minus, it would be 9 times 3, 27. Okay, no, they do match up. Okay, so 3 mi over 4 L square ei, and what I have in here is 9 L cube divided by 27. So please do check my algebra if I'm not making any mistakes. 9 times 3 and 27 cancel off, and what I've left, L square, L cube cancel off, leaving me with 1 L there. So that gives me MIL over 4 EI. And let's check. Yep. Which tells me that MI, so I'll write that in red now, MI is equal to 4 EI over L times theta I. Do you agree? And similarly, I can calculate all the other four values, which would be that mj is mi over 2. So that's simply equal to 2 ei over L times theta I. Q I is equal to I should have really written that down here. So mi is equal to 2 ei over L cube q. Sorry. Oh, mi is that, and this is mj. Qi, we have already found Qi is equal to 3 over 2 mi over L. So let's see what that would be. This and so 3 over 2 times this guy over L would be 6 EI over L square times theta I, and the negative of that would be at the other end. So we get minus 6 EI over L square times theta I. And let's make sure that it's the right direction. Yep. So so once again, I think what we let me summarize what we tried to do here. What we did last time was for case 1. Today looks like we've managed pick case 2. First, we realized that this is an indeterminate problem. We broke it up into two parts. Both of them were determinate, simply supported beam. We tried to find what would be the rotation for this problem at the right end. Okay, that's what we call theta j prime. Using the virtual work method by applying a unit moment at this point, and using the virtual work method, we found that theta j prime was mi L over 6 EI negative. And for alpha jj, we read off the value from the front cover of the table, but you can essentially use the same method. Using the virtual work, you can calculate alpha jj also. That came out to be L over 3 EI. We used compatibility to first then relate mj with mi. So all of this, first of all, only to relate mj to mi. Using those two things, we calculated the reactions. So now we have all the reactions. And then we took the bending moment diagram of the indeterminate structure by combining both of these, essentially both of these in the right amounts. We came up with this bending moment diagram. I picked the origin here and calculated the rotation at the left end by using again the virtual work method. And we found that theta I is equal to mi L over 4 EI. So I reversed that relationship. I expressed that as mi is equal to 4 EI over L times theta I, and used all the other four relationships, or the other three relationships, to find qi, qj, and mj. That's all that we did here. Make sense? At this point, can anybody tell me how can I put that in a matrix form? How can I express these four relationships in a matrix form? It's the same four forces and moments. The degrees of freedom right now are only theta I is non-zero. All the other degrees of freedom are 0. So we know that we can take all of these four coefficients. These are stiffness coefficients. And where do I put them? Second column, right? So put them here, and let's see if I can fit them. And the other three values in each row do not matter because the degrees of freedom corresponding to those columns are 0. So just being able to express these four relationships in the form of a matrix will help us out very shortly, as you will see, because now that we have case 2 done, we have case 1 also done. So you should be able to see, first of all, that case 3 is just a mirror image of case 1, right? And case 4 is a mirror image and a flipping of the signs than case 2. So in case 2, we apply a moment here, find the rotation. In case 4, we apply a moment at the right end and find the rotation here. So it's exactly the same problem. You can use the same stiffness coefficients, but take care of the signs appropriately. And when you do that, you can take all of those, this first column, this second column that we just calculated, and similarly the third and the fourth column can be computed for case 3 and case 4. And once you have all of that, then you can put them all together in a big matrix, a 4x4 matrix, which actually correlates the four stiffness, the four force and moment quantities with the four rotations and displacements. That's the big relationship that we really wanted. That relationship tells me that if I have a beam element, so combining cases 1 through 4, we get this system of equations, which I hope now you understand how we got there. If I have a beam element, no matter what displacement and rotation you tell me, you can say I have a displacement -1 at node I. I have a displacement +1 at node J. I have some rotation here, some rotation here. So no matter what the shape of the ultimately of the beam element, I can use this relationship to tell you exactly what the forces at the ends would be. Okay, and that is really useful when we are going to use this stiffness matrix for solving bigger problems. Can anybody tell me an analog of this relationship for the trusses? What was the relationship for the truss element problems that we came up with? Not the global stiffness matrix. It would be the element stiffness matrix for the truss element. You remember we said that we'll constrain ourselves to local coordinate system, and in the local coordinate system, the stiffness element stiffness matrix was just +1, -1, -1, +1, right? It was for truss elements. It was that simple. For beam elements, it's fairly more complicated. But now that we have done it for once and for all, we can use it again and again. We don't have to derive it ever again. Okay, so we'll use this relationship. This relationship is again something that will be constant for no matter which beam element you have. And this will serve the same purpose that the truss stiffness matrix did with the +1, -1, and so on. All right, so next time we'll assemble this, we'll solve a couple of beam problems, and we'll see how that goes. Okay.